In the last class, we have seen that how the energy liberated by a chemical reaction can achieve pumping or population inversion in a chemical, and why a chemical laser usually emits light in the infrared region of electromagnetic spectrum. And we also have seen that hydrogen fluoride was the very first uh, chemical laser that was developed in the year 1965. And following this, there has been operation of a host of chemical lasers, of which the most popular laser that was emerged, the lasers which have emerged as the most popular lasers are hydrogen fluoride and deuterium fluoride. We also have seen that hydrogen fluoride and deuterium fluoride, although they have attracted attention of military developers, but they have their issues, like the emission of hydrogen fluoride laser, which operates in the region of 2.6 micrometer to 3 micrometer range of wavelengths of infrared region of the electromagnetic spectrum. Actually, air causes significant absorption of light at these wavelengths. Therefore, it offers a challenge for its military application. The other laser, DF laser, deuterium fluoride laser, which emits light in the wavelength range spanning over 3.6 micron to 4 micron, is relatively better in the sense that air has very little absorption in this region of wavelength, and therefore, as far as transmission through atmosphere is concerned, this laser is a better choice. However, the challenge that this laser faces is because of its higher wavelength compared to that of HF laser. Because the higher wavelength focusability of this laser is less than this. And therefore, this is another challenge, because if you cannot focus the beam very tightly on the target, the power of its causing destruction would also be accordingly less. And as we would see later, that in this context, another laser, which is called chemical oxygen iodine laser, actually emerged as a source of light, which was ideal for military application. Which is ideal for military application, as it emits light at a wavelength of 1.3 micron, for which air has negligible resistance, and also because of its very small wavelength, its focusability is also much better. It can be focused very tightly on the target. Now, of these two lasers, hydrogen fluoride and deuterium fluoride, their principle of working is almost identical. And let us therefore focus on the principle of operation of hydrogen fluoride laser. So the operation of the hydrogen fluoride laser was first reported in 1967, and rapid development followed thereafter. By 1982, hydrogen fluoride lasers capable of delivering CW power, that is continuous power, exceeding even megawatt, was demonstrated. Megawatt coherent light. Coherent light of continuous power of megawatt is mind-boggling. And of course, you cannot generate this megawatt level of power. You generate it continuously, but you don't keep on producing this power at a continuous manner, in a continuous manner. This would be quite impractical. Even if it operates in a quasi-continuum manner. Say, the laser delivers output, say for, let us assume a very realistic figure, for 100 milliseconds. And then it turns off. Then maybe at a later time, it will again produce another pulse of 100 milliseconds. But the power is say 2 megawatt. Now, if you produce 2 megawatt power, optical power, coherent optical light for 100 milliseconds, then what will be the energy that will be confined within this time, 100 millisecond? It would be basically 2 into 10 to the power 6 watt, that is 2 megawatt. So what is joule per second into 100 millisecond? So 100 into 10 to the power minus 3 second. So this is equal to 2 into 10 to the power 5 joule. So 200 kilojoule energy will be confined in this pulse, almost continuous pulse. 100 millisecond is a very long time. So if this energy confined in this time is focused on the target, then it can result in exorbitantly high intensity that can just in a flash destroy the target with so much of energy, so much of intensity. So let us explore the principle of operation of this hydrogen fluoride. So the hydrogen fluoride laser is of course an infrared laser, as we already know now. The lasing originates from the transition between rotational vibrational levels of the ground electronic state of the molecule, similar to the operation of a carbon dioxide laser. So there will be many rotational vibrational transitions. So naturally, this laser will be a tunable laser like carbon dioxide laser. So how do you actually achieve this? Vibrationally excited hydrogen fluoride molecules are produced when atomic fluorine reacts with molecular hydrogen. So fluorine, atomic fluorine, upon reaction with hydrogen molecule, produces hydrogen fluoride molecule at an excited state. So this basically represents a vibrationally excited state of the product molecule. So let us delve a little deeper and try to understand that what are the transitions of this that would result in population inversion and in turn lasing. So let us consider this is the ground electronic state of hydrogen fluoride. And in this ground electronic state, these are few vibrational states which have been shown. So this is the ground vibrational state. This is the first vibrational excited state, which we call E1. Then V equal to 2, which we call E2. Then this is V equal to 3, which we call E3. So the first four vibrational levels, namely of vibrational quantum number 0, 1, 2, and 3, states of the hydrogen fluoride molecules were found to be populated as they are formed through fluorine hydrogen reaction. So in actual practice, once the molecules, HF molecule is formed, these four vibrational states have been found to be populated mostly. The others have negligible population. So we do not consider the other states. There are many states we don't consider, as most of the population have been found to be confined within this four vibrations. and the relative rates of their chemical reaction driven pumping have been measured to be this V3 is to V2 is to V1 is to V0 is actually 12 is to 20 is to 6 to 1. So now let us assume from this rate of excitation, what will be the number of molecules that would reside in these different vibrational states. So this is vibrational state 0. So its excitation probability, sorry, this is 0. So its excitation probability is 1. Rate, excitation rate 1. And the next one, that is V equal to 1, 6. Then this is 20, V equal to 2, and V equal to 3 is 12. And the others are very, very small. So now suppose we have 100, we have created 100 HF molecule following this reaction. That is F plus H2, which is result in the formation of HF plus H. So we have created 100 hydrogen fluoride molecules. So out of this 100 hydrogen fluoride molecules, how many molecules would be in the ground state? Not in the ground state, say in this state, N equal to V equal to 2 in this state. How many molecules will be there in this state? There will be 20 by 1 plus 6 plus 20 plus 12 into 100. Of this 100 molecules which has been produced, these many molecules will be in this state. So which is actually, if you work it out, it will be 20, 39 into 100. So this will be nearly equal to 51. So out of this 100 molecule, 51 molecule will be created in this state. And in the similar way, you can show that there will be 15 molecule in the first vibrational excited state and 31 molecule will be in the third vibrational excited state. At the ground state, there will be only 3 molecules. For this pumping rate, between which transitions there will be population inversion? For transition between E1 and E3, this has more population than this. So population inversion exists between these two. So population inversion exists between E1 and E0. Then population inversion exists between E2 and E1. Population inversion exists between E2 and E0. And also population inversion exists between E3 and E1. and also between E3 and E0. So population inversion as a result of this pumping through chemical reaction occurs on all the 5 transitions. However, spectroscopic rule forbids transition on all these 5 possibilities. See, the selection rule or the spectroscopic rule that guides this transition says delta V can be only 1. That is, due to transition, the change of vibrational quantum number can be only 1. It cannot be more than 1 or 0. Of course, it cannot be 0. So now you see, for the transition E1 and E0, E1 and E0, this condition is satisfied because the vibrational quantum number changed from 1 to 0. So that is the change is 1. So for this, the vibrational quantum number changes by 1, E1 and E0. So this is allowed. For E2 and E1, the quantum number changes from 2 to 1. So once again, this is 1. So this is also allowed. E2 and E0, the vibrational quantum number changes from 2 to 0. So delta V becomes 2. So this is not allowed. E3 and E1, the vibrational quantum number changes from 3 to 1. 3 to 1. So this is again 2. So not allowed. And E3 and E0, although there is population inversion 31 to 3, but vibrational quantum number changes here from 3 to 0. That is, the total change is 3. This is also not allowed. So transition is possible only for this E1 to E0 and E2 to E1. Although population inversion exists for three other transitions, the spectroscopic selection rule would not allow optical emission in these 3 transitions. So then, the lasing, as the population inversion exists between these 2, this and this, this and this, therefore, if you place this population inverted medium inside a cavity, you will, of course, achieve lasing, that is amplification of light on these 2 transitions. Of course, the stimulated emission that would eventually amplify light would be seeded by spontaneous emission that would occur in this, for this transition as well as this transition. And they will have, now all these vibrational levels have their rotational manifolds, so there will be numerous transitions from different rotational vibrational levels, meaning that emission can occur on a number of wavelengths. And that is why this laser is tunable. And its tunability, as I mentioned earlier, is from 2.6 micron wavelength to 3 micron. However, you must be thinking about how do you get atomic fluid, because this reaction is caused by atomic fluorine and molecular hydrogen. Fluorine plus hydrogen creates hydrogen fluoride in the excited state. See, this fluorine is usually obtained, is made available in its atomic form usually by striking a high voltage electric discharge in the SF6 gas in the vicinity of the lasing zone. So how do you do it? See, you first take SF6 gas and subject it to a discharge by applying the usual way, in the way a transversely excited carbon dioxide laser operate, TSCOP laser operate. You have two transverse electrode, you place SF6 gas and subject this to a high voltage discharge. In the discharge, as you know now, there would be always presence of electron. The electron will also have a varying range of kinetic energies, and when these electrons collide with some kinetic energy, collide with SF6 gas, SF6 molecule, then it can actually dissociate the SF6 molecule, SF5 and electron. Of course, the electron will now move with less kinetic energy, having supplied the energy of dissociation. And then there will be some other electron which will collide now with SF5 and dissociate it further. SF4 and electron with less kinetic, and so on. So you will produce avalanche of fluorine. Sorry, I'm extremely sorry. Of course, you will create fluorine, and SF4 also it collide with electron, and then SF3 plus fluorine, and so on. You will create avalanche of fluorine, and this fluorine is in atomic form, which will actually react with hydrogen and create hydrogen fluoride molecule in the vibrationally excited states, in a way that you create population inversion between some transitions for which a spectroscopic transition rule is allowed, and you create population inverted. You create coherent light at those wavelengths for which the transition is taking place. So we have seen that like CO2 laser, these lasers also can have many rotational vibrational transitions, and we have already seen the HF laser operate in the range of 2.6 to 3 micron, and if you replace hydrogen by that other heavier isotope of hydrogen, which is rarer, then the lasing window shifts from 3.6 to 4.4 micron. Although the atmosphere is more transparent at these wavelengths, the DF laser is still not very attractive for military application, as with increasing wavelength, the focal spot intensity decreases, so the intensity reduces at the target. We have already discussed this just a while ago. Let me also mention here that 2.2 megawatt class mid-infrared advanced chemical laser, which is abbreviated as Miracle, has been used in important laser weapon demonstration studies. Number of such demonstration studies which have made use of 2.2 megawatt emitted by a DF laser. This was 2.2 megawatt mid-infrared advanced chemical called Miracle has been used in important laser weapons demonstration studies. Notable here is that the missiles, multiple missiles, were shot down in a series of tests jointly conducted by the United States of America and Israel. However, I said that this wavelength, 3.624 micron wavelength, is much too large because the focusability, it cannot be very well focused, this high wavelength emission from DF laser. Although it has good transmission in the atmosphere, but the limited focusability is a challenge for its use in military applications. In this regard, chemical oxygen iodine laser, that is abbreviated as COIL, has emerged as a more ideal laser for military application. It is worth mentioning in this context of yet another electronic transition, chemical laser, popularly known as COIL. It is actually a chemical laser, but it is based on electronic transition, not vibrational transition. I'll come to this in a while. It operates at a much shorter wavelength simply because it is electronic transition, not vibrational transition. So the wavelength is much shorter because the energy gap between the transitions which is participating in this process of lasing is much well separated. Therefore, the light that is produced as a result of this transition would be much shorter in wavelength or higher in frequency. At this wavelength, atmosphere exhibits very good transmission. And this in conjunction with the tighter focusability at such shorter wavelength makes this laser more effective in destroying military targets than the longer wavelength DF laser and of course HF laser, which essentially has very poor transmission in the atmosphere. And this laser has a wavelength which is even shorter, smaller than that of hydrogen fluoride laser. So how does it work? A chemical reaction, you take an appropriate reactant, chemical reaction actually produces oxygen molecule in a metastable excited state. So this is the ground state of oxygen molecule and this is a metastable state. Metastable state means its lifetime is much too long. So it doesn't decay very fast from this level. Once it has been excited, it is long-lived and it stays there. This long-lived excited state oxygen molecules subsequently dissociate. This O2 metastable excited state, when it reacts with iodine, it actually supplies this energy and dissociate iodine into its atomic form. And this iodine is produced in electronically excited state. So, this is the ground state of iodine and it has been formed in its electronically excited state. So this is iodine in the excited state. It has been formed in the excited state, the iodine. So this transition results in emission of 1.3 micron wavelength. When, of course, this is integrated with a cavity, you generate coherent light at 1.3 micron wavelength, which is ideal for military application. However, the COIL laser is of extremely large size, meaning it has a very large footprint. If an army aircraft can be customized to accommodate such a laser, coil laser, which of course has happened, then suppose you have actually customized this aircraft to accommodate a coil laser. And upon sighting a missile, and upon sighting a missile in the media, which may be carrying, say, nuclear warhead, or it fires a giant pulse in the direction of the missile. And during the travel of this pulse, containing colossal amount of energy, the missile, however fast it moves, would appear to be at rest. It will be frozen in space because light travels with enormously high speed, and missile would appear to be frozen in space, and thus would strike the missile without any fail, and it will be a precision strike and destroying it just in a flash. So today you have seen how a chemical laser operates, how the energy that is liberated in a chemical reaction can result in the formation of the molecule in the excited state, allowing creation of population inversion, and when it is integrated with a cavity, it can easily amplify light, giving rise to coherent light at infrared wavelengths and even shorter wavelength, like which coil laser gives at 1.3 micron. It is of course infrared, but it is on the shorter, smaller wavelength side of the infrared. And you also have seen that how chemical laser can produce enormously high energy, and why they are so popular as in military application. I think I will stop here today.